This lecture is a continued discussion of generative probabilistic models for text clustering. In this lecture, we're going to finish the discussion of generative probabilistic models for text clustering. So this is a slide that you have seen before. And here we show how we define the mixture model for text clustering and what the likelihood function looks like. And we can also compute the maximum likelihood estimate to estimate the parameters. In this lecture, we're going to talk more about how exactly we're going to compute the maximum likelihood estimate. Now, as in most cases, the EM algorithm can be used to solve this problem for mixture models. So here's the detail of this EM algorithm for document clustering. Now, if you have understood how EM algorithm works for topic models like PLSA, and I think here it will be very similar. You just need to adapt a little bit to this new mixture model. So as you may recall, EM algorithm starts with the initialization of all the parameters. So this is the same as what happened before for topic models. And then we're going to repeat until the likelihood converges. And in each step, we're going to do E step and M step. In the M step, we're going to infer which distribution has been used to generate each document. And so we have to introduce a hidden variable ZD for each document. And this variable could take a value from the range of 1 through k, representing k different distributions. And more specifically, basically, we're going to apply Bayes' rule to infer which distribution is more likely to have generated this document, or computing the posterior probability of the distribution given the document. And we know it's proportional to the probability of selecting this distribution P of theta I and the probability of generating this whole document from that distribution, which is a product of all the probabilities of words for this document, as you see here. Now, as in all cases, it's useful to kind of remember the normalizer or the constraint on this probability. So in this case, we know the constraint on this probability in the E step is that all the probabilities of Z equals I must sum to 1, because the document must have been generated from precisely one of these K topics. So the probability of being generated from each of them should sum to 1. And if you know this constraint, then you can easily compute this distribution as long as you know what it is proportional to. Right? So once you compute this product that you see here, then you simply normalize these probabilities to make them sum to 1 over all the topics. So that's E step. After E step, we would know which distribution is more likely to have generated this document D, and which is unlikely. Right? And then in the M step, we're going to re-estimate all the parameters based on the inferred Z values, or inferred knowledge about which distribution has been used to generate which document. So the re-estimation involves two kinds of parameters. One is P of theta, and this is the probability of selecting a particular distribution. Before we observe anything, we don't have any knowledge about which cluster is more likely. But after we have observed these documents, then we can collect the evidence to infer which cluster is more likely. And so this is proportional to the sum of the probability of Z sub dj is equal to I. And so this gives us all the evidence about using topic I, or theta I, to generate a document. And we put them together. And then again, we normalize them into probabilities. And then, so this is for P of theta sub I. Now, the other kind of parameters are the probabilities of words in each distribution, or in each cluster. And this is very similar to the case of PLSA. And here we just put the counts of words that are in documents that are inferred to have been generated from a particular topic, theta I here. And this would allow us to then estimate how many words have actually been generated from theta I. And then we normalize again these counts into probabilities so that the probabilities on all the words would sum to 1. Note that it's very important to understand these constraints as they are precisely the normalizers in all these formulas. And it's also important to know that the distribution is over what. For example, the probability of theta is over all the k topics, and that's why these k probabilities will sum to 1. Whereas the probability of a word given theta is a probability distribution over all the words. So there are many probabilities, and they have to sum to 1. So now let's take a look at the simple example of 2 clusters. I have 2 clusters. I've shown some initialized values for the 2 distributions, and let's assume we randomly initialize 2 probabilities of selecting each cluster as 0.5, so equally likely. And then let's consider one document that you have seen here. There are 2 words, 2 occurrences of text and 2 occurrences of mining. So there are 4 words together. And medical and health did not occur in this document. So let's first think about the hidden variables. Now, for each document, we must use a hidden variable. Right? And before in PLSA, we used one hidden variable for each word, right? Because that's the output from one mixture model. So in our case, the output from a mixture model or the observation from mixture model is a document, not a word. So now we have one hidden variable attached to the document. Now the hidden variable must tell us which distribution has been used to generate the document. So it's going to take 2 values, 1 and 2, to indicate the 2 topics. So now how do we infer which distribution has been used to generate the D? Well, it's to use Bayes' rule. So it looks like this. In order for the first topic, theta 1, to generate the document, 2 things must happen. First, theta sub 1 must have been selected. So it's P, given by P of theta 1. Second, it must have also been generating the 4 words in the document, namely 2 occurrences of text and 2 occurrences of mining. So that's why you see the numerator has the product of the probability of selecting theta 1 and the probability of generating the document from theta 1. So the denominator is just the sum of 2 possibilities of generating this document, and you can plug in the numerical values to verify indeed in this case the document is more likely to be generated from theta 1, much more likely than from theta 2. So once we have this probability, we can easily compute the probability of z equals 2 given this document. How? Well, we can use the constraint, right? So that's going to be 1 minus 100 over 101. So now it's important to note that in such a computation, there is a potential problem of underflow. And that is because if you look at the numerator, the original numerator, and the denominator, it involves the computation of a product or of many small probabilities. Imagine if a document has many words and it's going to be a very small value here. It can cause the problem of underflow. So to solve the problem, we can use a normalizer. So here you see that we take an average of all these 2 distributions to compute another average distribution called theta bar. And the average distribution will be comparable to each of these distributions in terms of the quantities, the magnitude. So we can then divide the numerator and the denominator both by this normalizer. So basically this normalizes the probability of generating this document by using this average word distribution. So you can see the normalizer here. And since we have used exactly the same normalizer for the numerator and the denominator, the whole value of this expression is not changed. But by doing this normalization, you can see we can make the numerators and the denominators more manageable in that the overall value is not going to be very small for each, and thus we can avoid the underflow problem. In some other times, we sometimes also use logarithm of the product to convert this into a sum of log of probabilities. This can help preserve precision as well. But in this case, we cannot use logarithm to solve the problem because there's a sum in the denominator. But this kind of normalizers can be effective for solving this problem. So it's a technique that's sometimes useful in other situations as well. Now let's look at the M step. So from the E step, we can see our estimate of which distribution is more likely to have generated the document D, right? And you can see D1 is more likely from the first topic, whereas D2 is more likely from the second topic, etc. Now let's think about what we need to compute in the M step. Well, basically we need to re-estimate all the parameters. Let's first look at the P of theta 1 and P of theta 2. Well, how do we estimate that? Well, intuitively, you can just pull together these Z probabilities from E step, right? So if all these documents say, well, they're more likely from theta 1, then we intuitively would give a high probability to theta 1, right? So in this case, so we can just take the average of these probabilities that you see here, and we obtain a 0.6 for theta 1. So theta 1 is more likely than theta 2. So you can see probability of theta 2 would be naturally 0.4. What about these word probabilities? Well, we do the same, and the intuition is the same. So we're going to see, well, in order to estimate the probabilities of words in theta 1, we're going to look at which documents have been generated from theta 1. And we're going to pull together the words in those documents and normalize them. So this is basically what I just said. More specifically, we're going to, for example, use all the counts of text in these documents to estimate the probability of text given theta 1. But we're not going to use their raw counts or total counts. Instead, we're going to then discount them by the probabilities that each document is likely being generated from theta 1. So this gives us some fractional counts. And then these counts will be then normalized in order to get the probability. Now, how do we normalize them? Well, these probabilities of these words must sum to 1. So to summarize our discussion of generative models for clustering, well, we show that a slight variation of topic model can be used for clustering documents. And this also shows the power of generative models in general. By changing the generation assumption and changing the model slightly, we can achieve different goals and we can capture different patterns in text data. So in this case, each cluster is represented by unigram language model, word distribution, and that's similar to a topic model. So here you can see the word distribution actually generates a term cluster as a byproduct. A document is generated by first choosing a unigram language model and then generating all the words in the document using this single language model. And this is very different from, again, topic model, where we can generate the words in the document by using multiple unigram language models. And then the estimated model parameters will give both a topic characterization of each cluster and a probabilistic assignment of each document into a cluster. And this probabilistic assignment sometimes is useful for some applications. But if we want to achieve harder clusters, mainly to partition documents into disjoint clusters, then we can just force a document into the cluster corresponding to the word distribution that's most likely to have generated the document. We've also shown that the EM algorithm can be used to compute the maximum likelihood estimator. And in this case, we need to use a special normalization technique to avoid underflow.